Chapter 2, Force Vectors. All right, everyone. Today we are going to learn about something super useful that helps engineers build things like bridges, towers, or even rockets. It's called force vectors. Now imagine you are pulling a toy car with a string. If you pull straight ahead, it moves straight. But if you pull to the side, it moves sideways too. This pull is what we call a force, and when we need to explain exactly how much you are pulling and in which direction, we use something called a vector. A vector is like an arrow. It shows how strong your pull is and which way it goes. Some things are simple numbers, like your age or the temperature. We call them scalars because they just have a number. But when something has a number and a direction, like pulling a car or flying a kite, we call it a vector. When we draw it, the arrow's length shows how strong it is, and where it points shows the direction. If you pull harder, the arrow gets longer. If you pull softer, it gets shorter. You can also pull in the opposite direction, and the arrow will flip the other way. When we pull or push on something from two directions, we can add these forces together. It's just like combining two ropes pulling on a box. There are two ways to do it: using a shape called a parallelogram, or simply putting the arrows head to tail like a train of arrows. Sometimes forces go in exactly the same direction, like two people pushing a car forward. Then we can just add the numbers. But when they go in different directions, we have to think about both the number and the direction. That's why we use the parallelogram or the triangle way to add them up. In engineering, we often need to find the total force or split one force into two smaller pushes along two directions, just like pulling a box on the floor where one rope pulls it sideways and another pulls it forward. We can use angles and simple math tricks like the law of sines and law of cosines, just like when you solve triangle puzzles. When you have more than two forces, you don't have to keep drawing big shapes. You can just break every force into two simple pieces, one going sideways, x direction, and one going up and down, y direction. Then you add up all the sideways forces together and all the up-down forces together. When you're done, you only have two forces left to deal with. And you can use the Pythagoras rule, the one with the a squared plus b squared equals c squared, to find out how strong the total pull is and which way it goes. Sometimes we also have to work in three directions: sideways, x, forward backward, y, and up and down, z. It's like knowing where a drone flies in space. To make it easy, we write the force using three letters called I, J, and K. Each letter tells how much force goes in each direction. We can still use the same triangle thinking, but now in three directions. When we want to know how much total force there is, we do the square root of the sum of squares, like magic math. There are also special angles called direction angles, which tell us how much a force is pointing along each direction, like how steep or sideways your rope is when pulling. These angles help us describe forces very precisely. To solve problems easily, engineers follow steps. First, break every force into pieces along x, y, and z. Second, add them up. Third, use square roots and angle tricks to find out how strong the total result is and which direction it goes. It's like solving a Lego puzzle, but with invisible arrows. So, to wrap it up, vectors help us know how strong a push or pull is and where it goes. We can add them, split them, and even figure out the total result in two or three directions. These tricks are super helpful to make sure bridges stay up, rockets fly straight, and towers don't fall. Just like balancing your Lego tower, only now it's with math and arrows.